Hello and welcome to
Small Talk
about the big issue. I'm Kiara.
And I'm Lorraine. And hopefully this episode title will have piqued your interest. And we've got some answers for you.
So I think to understand if we really are on the brink of an ice age, we need to understand what drives our climates. And spoiler alert, you know we're talking about the ocean today. So I'll spend the first part explaining how ocean currents form and what responsibility they have in shaping our climates.
And then I'll present some very cool and fascinating science with some pretty dramatic implications.
I think that sums it up. Let's not reveal too much too soon. So before we answer the question, are we on the brink of an ice age? I think we need to address a few things. So far, we've mostly talked about how climate change influences, well, the level of our oceans, but also the acidification of our oceans. What we're going to talk about today is slightly different in the sense that now we're going to talk about how the ocean impacts our climate. And I think that's very interesting. Doing research for this episode brought me straight back to an oceanography class that I took when I was in northern Norway for my Erasmus. And we learned all about how currents formed and how they distributed heat all around the Earth. So I'm really excited to dive right back in. There's multiple factors involved when it comes to ocean currents. They're a combination of the effects of wind, of temperature, salinity, but also of the Earth's rotation and of gravity. So there's a lot of forces at work, and we'll try to keep it as simple as we can, because I remember a lot of people being quite lost during that oceanography lecture. It wasn't a mandatory lecture, and I remember at the end we were only 5 students in the lecture hall every week.
Which is crazy because the ocean is such a key part of understanding the Earth. As you said in the first episode of our ocean unit, David Attenborough says you can only understand life on land if you look at the ocean. And I think I haven't had an oceanography lecture as part of my curriculum, but I'm realizing as we've done research, not just for the ocean unit, but for all the other episodes we did, just how central the ocean is in regulating our climate, both without us messing with it, but especially when we start to mess with it.
Good point. I think what's important to know is that surface currents are mostly driven by wind. However, deeper currents, because the oceanic currents happen on multiple levels to form an entire conveyor belt, which is something I want to get to very shortly.
Okay.
But density is a driving force of currents. And I think it's the first thing that we need to introduce. Lorraine, do you want to introduce the concept?
Yes, I can. Density is a measure of an object's mass per unit of volume. So an object's mass, we often think of as its weight, although maybe the equivalence is not completely, some physicists might not be very happy. And the volume is how much space it takes up. So if you think of things that have very small density, things like polystyrene or an air balloon, it's very light. But things like a lot of metals are very dense because even like a small coin can weigh quite a bit.
To compare the density of different matters, what you need to do is take the same volume of each matter and compare its weight. It will give you an indication of its density. If you fill a 1 liter water bottle with flour, or if you fill it with oil, it will not have the same weight, and it will, you can try this with a lot of things at home and then compare which one weighs more.
Little at-home experiment. But linked to the ocean, if you fill up, and maybe this would be a fun experiment to try at home, I haven't done this. If you fill up a 1 liter water bottle with water from your tap, and then another one with water from your tap plus a load of salt, which one would be denser?
The one with the salt.
Yes, and I think that's linked to ocean currents, right? How they work.
Yes, absolutely. Because, well, as Lorraine hinted towards, there's multiple things that can affect water's density. So the ocean does not have the same density all around the globe. There's some parts that will be more dense, other parts that will be less dense. And this is usually a matter of temperature and salinity, which is how much salt the water holds. So typically, cold water is denser than warm water. At the same time, salty water is denser than fresh water. So can you imagine a combination of cold and salty water is going to be a lot denser than warm, fresh water.
Uh-huh.
So the deep currents are mostly driven by cold, salty water sinking into the deep ocean. And so as this water sinks, it creates space for new water to come from the surface. So that's usually what drives these currents around the world, is that usually around the poles, you see the sinking of very big, cold and salty water masses, which leaves some space for hotter water from the tropics to flow to higher latitudes to take up the space that water took up.
And this is also because at the poles you get ice formation, and ice doesn't trap as much salt. And so essentially the leftover water is left with more salt to deal with.
Definitely. So this is tightly linked to the fact that in the Arctic or Antarctic, there's a lot of ice formation. Sea ice forms from seawater, but it doesn't contain any salt. So the more seawater freezes, the more salt gets sent back into the ocean, which creates very cold, salty water. So as soon as the water becomes cold and salty enough, it sinks down to the deep ocean, and warmer, less dense water from the Gulf Stream or from the tropics rushes in to replace the water that sinks. And so this entire motion is a very dynamic conveyor's belt, literally, that brings warm water from the tropics towards the poles, where then it cools down and then travels back to the tropics, but deep down in the ocean.
It's like those escalators. They just kind of push one another and go around and around.
And so we have a really big one here in the Atlantic Ocean. It's called the Atlantic Meridional Ocean Circulation. You can shorten it and call it AMOC, if that's okay with you. And this and the Gulf Stream, which is another current that kind of flows parallel to it, is the reason why Europe is enjoying a relatively mild climate compared to its latitude. I don't know if you've ever realized, I think it struck me as a child, that we're quite high up compared to, for example, the US.
I know.
As a comparison, for example, Florence in Italy is at the same latitude as Toronto.
Oh, whoa, I had never noticed it was that drastic.
I can tell you that the winters in Italy are not the same as in Toronto.
Yeah, I'd never noticed it was so different.
So that's thanks to one of those currents called the Gulf Stream, which is also tightly linked to the Atlantic Meridional Ocean Circulation, that brings all this tropical heat in the ocean's surface layer towards the poles, towards Europe. However, we have a problem. Because, of course, we're here to talk about problems, right? Because we want to solve them. So that's always a good step to start with. The water at the poles is getting less dense. Why? Well, because the poles are warming. The Arctic is warming twice as fast as the entire world, which means its water is as well. And warmer water is less dense, as we've just said. So it makes it really hard to sink. But this cold water sinking was what was driving that thermohaline circulation. Thermohaline is maybe a complicated word, but it basically just means thermo being heat and haline is salt. So it's this combination of the effect of heat and salt on the ocean circulation. So because of global warming, this global oceanic current is threatened to slow down. Because Greenland's ice sheet is melting because of warmer air, well, there's more fresh water into the North Atlantic. And we said again that fresh water is less dense than salty water. Warm water is less dense than cold water. So we're adding just a lot of warm water, a lot of fresh water into the pole, which completely disrupts that phenomenon.
So it's like we're breaking the motor that was driving this hot current towards Europe in the Atlantic.
If enough water stops sinking, then the AMOC will weaken. And that's another climate tipping point. It would be the collapse of the AMOC, because at some point not enough water will sink, and so this enormous global current that makes, for example, life in Europe right now pretty agreeable would stop. When this happens, Norway could see a drop in its temperatures of up to 20 degrees within 1 century. There's one good news, though. The Arctic would regain a lot of sea ice, so the polar bears might be saved.
Yeah, but that means that all the ecosystems that are below the Arctic in the northern hemisphere would have to migrate southwards very, very fast. I think, we'd be overcompensating in a way that's not necessarily solving issues other than, you're right, for the polar bears.
Definitely not. And this is a very local issue because the global temperatures would still be increasing. The rest of the world would still be warming. This is only an issue for Europe. But at the same time, we save the polar bears. We all have to leave Europe. But global warming keeps happening because we don't stop our emissions. The heat would just build up at lower latitudes, which
would leave a smaller window of survivable, livable land, for example.
It would increase the heat stress in these regions. This has dramatic consequences. It would, for example, deprive the Amazon rainforest of most of its rainfall. And this would certainly lead to the collapse of another tipping point, which is the Amazon rainforest, which will turn it into a grassland. So no carbon sink anymore. There's a lot more consequences to this, like the weakening of the African and Asian monsoons, just a lot less rainfall in general because a lot of snow would be falling in higher latitudes.
So a total deregulation of the climate, not just in Europe or the Northern Hemisphere, but really impacting everywhere.
So the question is, how likely is this going to happen? How likely are we to experience an ice age in Europe anytime soon? Well, the latest IPCC report stated that the AMOC is very likely to weaken over the 21st century due to climate change. However, it's really hard to measure the strength of the AMOC, and it's not been done consistently throughout these past decades. So it's very hard to find confirmation of such a decline, and the current projections from the same report are that the AMOC is unlikely to stop or collapse before at least the year 2100.
Which is still very, very soon. That's potentially within our lifetimes.
So this is all I know for now, but I've been told, Lorraine, that you might have more up-to-date information about the AMOC collapse.
So I do. And again, this is, I think, similar to the previous episode on ocean acidification, where we've got new ways of measuring things that tell us just how disrupted the ocean is. And the article that I wanted to talk about today is called Physics-Based Early Warning Signals Shows the AMOC is on Tipping Course. And it was published in 2024 by a team of scientists, actually 3 scientists in the Netherlands, led by René van Westen. And it's very cool science with very alarming results. Now, Kiara, you perfectly introduced the AMOC, so I'm skipping through my notes here. But I want to reiterate that the AMOC is a climate tipping point that we're particularly concerned about because it could undergo a very fast change under a slowly developing forcing. And in this case, a very important forcing is the amount of fresh water that's being added in the North Atlantic. Because the Greenland ice sheet is melting, glaciers on land are melting. So we've discussed how problematic it is for many reasons, but one of the reasons is because it's disrupting this AMOC flow. And so as you mentioned, Kiara, it's difficult to measure the AMOC. We've been doing it only since 2004, but we can use proxy methods like the sea level temperatures to allow us to go back to 1950s, and we can see that the AMOC has weakened. And if we use further proxies and other methods, we can see that the AMOC has changed abruptly in the geological past. So it's possible for it to undergo these very rapid changes. So it's not just a theoretical concern that we have here, potentially a very real one. But as you said, this is still a very difficult, huge conveyor belt to measure. And so far we've used mostly statistics to predict and study when or what factors would influence this tipping point. But these aren't always reliable. And so what the authors of this study did, and that's so fascinating, is that they found a physics-based early warning system. And what that means is that we can measure something else that will tell us how close we are to the tipping point before it tips. And this is crucial.
That's crucial, and that's incredible that they found this. I'm really eager to hear what they found out.
So this early warning system is the freshwater input in the North Atlantic. And so their work is based on the Community Earth System model. It's this complex global model, and crucially, it has really good resolution in the ocean. And they started working with pre-industrial conditions, so before we started messing with the climate and the ocean. And all they did is that they modeled what would happen if they gradually and incrementally, so little by little, and I'll spare you the physics here, but little by little, increased the freshwater input from the North Atlantic. So they're not tweaking the atmosphere, the greenhouse gases, they're just seeing what happens if they keep on putting more and more freshwater in the North Atlantic.
Which is bound to happen with the current rate of global warming.
Which is happening with the current rate of global warming. And what they find is a gradual decrease and then a collapse
Oh,
1,750 years after the models start.
so when does the model start?
So these years aren't linked to our time. It's just they started with pre-industrial conditions. That would be year 0. And then they linearly added more and more water for about 2,000 years. But in the year 1750, that's when they see a collapse of the AMOC.
So what does that mean applied to us?
Well, first, let me tell you how dramatic the collapse is. The AMOC decreases 5-fold in 100 years. So the current slows down to basically almost nothing in this very short amount of time. And as a result, as you said, Kiara, there's a cooling of the northern hemisphere with very sharp temperature drops in Western Europe. And so it's funny that you mentioned your Norway Erasmus in this episode, because I thought of you as I was reading the article. The example they give is that February temperatures for Bergen in Norway would drop by about 3.5 degrees Celsius per decade, which again is very rapid cooling.
Wow.
And then, as you said, the southern hemisphere, on the other hand, warms a little. And this is because there's less heat exchange happening between the hemispheres. So the slower the AMOC is, the more heat can accumulate in the southern hemisphere.
Because the AMOC basically just redistributes the heat throughout the earth. And if it stops, well, the heat just builds up at the tropics.
Exactly. Another implication is for ice coverage. If the AMOC stops, the Arctic sea ice pack would descend down to 50 degrees north at its lowest, which is when spring starts. So basically, waters around where we live, Kiara and I, would be covered in ice.
Okay.
So we would be living in a very, very different world. And as we've mentioned before, and I think this is really a key concept, the albedo feedback, this idea that the more ice there is, the whiter it is, the more solar radiation gets reflected back into space, the cooler things get. So again, a positive feedback loop, making it colder and colder in Europe. And on the other hand, you'd see the opposite trend in Antarctica in the southern hemisphere.
How so?
In the sense that because the southern hemisphere would be warming, the Antarctic sea ice would be retreating and you'd get less ice. So I don't know if there aren't polar bears in the Antarctic, I don't think, but there are loads of, I'm pretty sure.
There's penguins.
But there's penguins. So the Antarctic penguins would suffer. So what we can conclude from this is that the freshwater input in the North Atlantic is an important indicator of the stability of AMOC. And so this led them to choose this indicator of the AMOC tipping point, which is the AMOC-induced freshwater transport at the southern boundary of the Atlantic. What that means is basically the amount of fresh water that the AMOC can bring back to the southern hemisphere. And what they saw is that it dropped very close to the AMOC collapse that they modeled. It dropped in the model year 1732, so roughly 25 years before the tipping point of the AMOC.
So does that mean the tipping point could be 25 years away?
So it means that when you see this freshwater transport at the southern boundary of the Atlantic drop, potentially when it hits a minimum, yes, you're 25 years away from the AMOC collapse.
So is it now that we're 25 years away?
No,
Okay.
but this is the next step. So,
Okay.
Can we measure this freshwater transport at the southern boundary of the Atlantic? The answer is yes.
Okay.
And where are we? The answer is it's decreasing. And so while we don't know exactly where the minimum is or could be, the fact that we're decreasing means we're going towards a tipping point.
So the tipping point is just getting closer,
Exactly.
which was in the title of the article. AMOC is on its tipping course. So there we have our answer.
And keep in mind that the model that they used didn't tweak carbon emissions or any greenhouse gases.
Yeah.
So actually, the impact of climate change forcing could mean that we're actually much closer to this collapse than we're able to determine for now. So the answer to our question, are we on the brink of an ice age, is actually, well, we're heading towards it. We're getting close to the tipping point where the AMOC collapses. And very rapidly afterwards causes this ice age in Europe. And this global disruption of climates, I think this is important to mention. The ice age would be in Europe, but the rest of the world would be heavily impacted because we wouldn't have, as you said, Kiara, this heat redistribution that evens out somewhat the global temperatures.
So I think these next few years will be crucial in terms of developing that model and trying to pinpoint when exactly this could happen. But I also think this is not an excuse to wait for the science to tell us when to prepare for it. I think it's pretty obvious that we have to start now to prevent it from happening. If models are already showing that we're leaning towards an AMOC collapse, that it's already getting slower.
And I find this a bit scary because we know that if we cut our carbon emissions, the temperatures aren't automatically going to start dropping.
No.
They might increase for a bit longer. And I think Kimberly Nicholas had said the system would respond faster than we once thought. But
there's still a lapse.
There's still a lapse.
Yeah.
And so that means that even if we were to take really effective climate action right now, the Greenland ice sheet and the glaciers all over Europe would keep melting. And so really, it feels like this is a very, and I mean everything about climate change is, but a very time-sensitive issue where we need to stop we need to stop carbon emissions so the temperatures stop rising, so we can preserve the Greenland ice sheets for many, many reasons, one of them being maintaining this AMOC.
Absolutely. What's important to say is that most of these tipping points, or even like the planetary boundaries that I talked about in the last episode, before you reach this state of no return, which is usually the tipping point, there is possibility of reversal. And I think if you're listening to this, you probably want to be reassured a little, and you can trust the Earth, and especially the oceans, to return back to their natural state shortly after we stop disturbing them.
If we do so before the tipping point.
So it's a mix between acting fast, but also to you listening, I think you're quite sensitive to the climate change conversation. And I think it's something to be aware of so that you don't feel that our fight is doomed.
See, this is the thing. I think something I've maybe come to terms with through doing this podcast is that talking about climate change is facing the fact that we have already destroyed so much, and there's so much that's lost and that we may never get back, as we discuss in these tipping points. And I hope that, the episode on sea level rise and preserving heritage sites and other episodes that we've done show just how much there is to save and how much action we have to do, and we know how to do. Like, we know
how to stop ocean acidification. We know how to stop sea level rise.
Yeah, we know how to do it. We have so much technology, so much science, so many ways of measuring things. What seems crucial now is implementing these changes. And I think that's a whole nother unit. And I think we've planned for a unit like this. Like, how do we
effectively implement climate solutions?
Exactly. Because a lot of debate that I've had, and we're getting a little bit off topic, so I'll keep this really short, but a lot of debate I've had with people is this a top-down solution? Do we expect governments to impose climate-friendly regulations, or should individual people pressure governments? This is a whole other topic. I think we should stop here.
I love that you mentioned this.
This is just, maybe a teasing for a future unit.
Absolutely. Well, thank you for sticking around until the end. As usual, if you have any comments, questions, or feedback, feel free to write a comment or send us an email at smalltalk.bigissue@gmail.com. See you next time. Goodbye. We fact-checked this episode and wanted to clarify a few things. We first would like to rectify what AMOC stands for. I said it is the Atlantic Meridional Ocean Circulation, when in fact it stands for Atlantic Meridional Overturning Circulation. We would also like to define forcing, which is a term Lorraine used a couple of times without explaining it. In the context of climate change models, forcing is a kind of pressure that is applied to a system. Here, it is the gradual addition of fresh water into the northern Atlantic, impacting the flow of AMOC. Finally, Lorraine was correct. There are indeed no polar bears in Antarctica. That's it for this week. See you next time.